All right. So there's a little bit of confusion with some of the people that showed up today, but kind of clarify, I did post, kind of replace the old seating chart with a new one. So I separated up into two groups. Group one, this week will be showing up Monday, Friday. Next week, group one would only be showing up Wednesday. This week, group two can show up Wednesday. Next week, you could show up Monday to Friday, right? And we kind of alternate that way for the rest of the semester because everybody on this list said they wanted to show up to in-person classes. There was no way for me to get it so I could kind of have everybody be able to show up twice a week as of right now. If people kind of drop out throughout the semester, maybe that will be possible. But for now, we're going to stick with these two groups, okay? I'm going to shut the door here real quick. All right, so last class, we left off talking about means, medians, and modes, okay? And also kind of talked about some different types of distributions. So we had the normal distribution, we had left, right skewed, and I said there was a reason why they were called left and right skewed. The way I said you could remember it last class was if it had a long right tail, that was a right skewed. If it had a long left tail, when we graphed that distribution, I said it would be a left skewed. But there's actually another reason as to why. So we ended last class, I also showed you those small little data sets, like 5 numbers, where I showed you how if instead of 10, it changed to 100, it greatly influenced the mean, it increased it by a lot, but it didn't impact the median. So if we had an example where the mean was exactly equal to the median, that would be what we would call that symmetric or that normal distribution, okay? If instead we had a really long right tail, which would represent that there's some really extremely high values in that data set, well, those really high values will pull the mean to the right or increase the mean, and so, but they won't impact the median near as much, so they would pull that mean to the right of the median, right? So if the mean is to the right of the median or greater than the median, that's why we call that a right skewed distribution, right? Or that's kind of another property. So even if I didn't show you the distribution right here, and I just told you what the mean and the median were, if I told you the mean of a data set was 50 and the median was only 20, right? So the mean would be greater than or to the right of the median, you would automatically know that's a right skewed distribution, even without seeing the actual distribution graph. Similarly, if we've got a long left tail, a really long left tail, we have a lot of really small values. It's kind of the same effect. Instead of increasing the mean there and not impacting the median as much, it's going to decrease the mean a lot, but not impact the median near as much. And so we'll end up with the mean being the left or less than the median, right? Why does it keep switching in class? All right. So if we have the mean to the left median, that's why we said we have a left skewed distribution, okay? Any questions on that? So even if I didn't show you these distributions, you should be able to, if I gave you the values of the mean and the median, if the mean is less than the median, it's a left skewed distribution. If the mean is to the right or greater than the median, it's a right skewed distribution, okay? Any questions before we keep moving from that? I know I was kind of referencing some stuff we did last class. So hopefully we can kind of remember what that was. But from here, we're going to leave measures of central tendency, right, and start to talk about measures of dispersion, or kind of think about this measures of variation, right? How varied is the data? How much variation exists in that data set? Okay? So if we go back to this example data set we were using last class where we had commute times of 7 different employees, all we're going to do to get the range of a data set is take the maximum value and subtract the minimum, or largest minus the smallest, right? So here it looks like we've got 90 is the maximum and 20 is the minimum. So all we do is 90 minus 20, which gives us that value of 70, okay? Now, you can kind of imagine if I had a data set that looked like this, but instead every single person's commute time was 20, except for the one person who had a 90-minute commute time, the range, so those of you on Zoom probably still see the slides, but for some reason this thing's switching. Let's see if I can figure out why real quick. I'm going to stop share. That's the one. So we're still using that one. Hopefully it stops doing this in class. Let's try doing the share thing again. Hopefully this time I won't keep switching. All right. So you can imagine if we had that data set with all 20s but 190, the range, right, would still be 70 because the maximum and the minimum would still be the same. But that second data set where everyone else's commute time was 20, well, there's not near as much variation in that data set, right? So the range does capture some of that, dispersion, or it gives us some information, but it doesn't really give us as much information as some other measures we have that are a lot more useful, right? That would allow us to distinguish between data sets that have the same range, but one of them would have all 20s are all the same value. Well, if it's all the same value, that's not much variation in the data set. It's only that one that would kind of be driving that range to up. So that measure that we're going to use is called the variance. Okay. So I'll walk us through this formula. I'll kind of give you kind of what all this notation means, and we'll think about what influences the variance, right? And kind of what it's trying to tell us. So sigma squared, that's our population variance, right? And the way that we're going to calculate that, there's this summation sign. So all this means is whatever is to the right of that sum sign, summation sign, do this mathematical operation for every single observation. And then once you do that, add up all those values, right? So for every single, whatever variable x you're looking at, look at the very first observation, subtract from whatever that value is of that first observation for that variable, subtract from that the mean, right? This mu, this is our population mean. So for each observation, we'll say what we'll call this is that observation's deviation from the mean, right? Or just the difference between that value and the mean. Once we find that deviation from the mean, we'll square it, write that number down, go to the next observation. So for the second observation, take that value, subtract the mean, and then square that. Continue to do this for every observation until we get to capital N represents the total number of observations in a population data set. So we'll keep doing this process until we get to the very last observation. Once we get there, then we'll add up all those values that we found. Once I add up all those values, the last thing I have to do is divide by the total number of observations in that population data set. Okay? So I'll walk through some examples here in a second with some actual data, but this is kind of just talking through what this formula is telling us. Now, we also have the sample variance, right? Now, one thing that's a little bit different here, it's the exact same process. The only thing that changes are, we're not using the population mean, we only have a sample mean now. Right? That's why it's a sample variance. And instead of the total number of observations in the population, we're using lowercase n, which is the total number of observations, lowercase n, which is the total number of observations in that sample data set. Okay? Sorry, we're having issues in class right now with the screen, so that should take care of it. If I need to use that later, I can plug it in. So, the only difference is we're using that sample mean and we're using lowercase n, which is the number in that sample. However, in the denominator, we're not just dividing by n now, we're dividing by n minus 1. So the reason as to why we're doing this, at this point in the class, I'm not going to go too in depth into it. It'll become a little more apparent once we get to things like hypothesis testing and confidence intervals, because that will be when we're dealing just with sample data. But if you want kind of just a general description as to why we're doing this, and I'm not going to like quiz you on this or make you have to give a really great description. But essentially, when you only have a sample, it's going to be biased from whatever the true population value actually is. And so to correct for that bias, we kind of divide by n minus 1 instead of n. So like I said, we'll go a little bit more, I think it'll make a little more sense once we get, quite a bit into the semester. But for now, just know that there is a difference between how we calculate the population and sample variance. And that difference is you don't just divide by n, you divide by n minus 1 for the sample. Okay? So if I divide by n minus 1 instead of n, what would that kind of do to the variance? So if instead of dividing by n, I divide by n minus 1, I'm dividing by a smaller value. So if I divide something by a smaller value, my resulting answer will be a little bit higher, right? So it's always going to kind of overstate or kind of inflate that sample variance a little bit to account for the fact that there is already a bias built into it because it's not the population data. Okay? But the exact same process really is what we were doing for that population variance. So, and then we've got here, the units will just be whatever the unit is of the variable you're using. So the units of the variance will just be, if I'm dealing with income data, it's going to be dollars. If I'm dealing with height data, it's going to be inches or feet, however I'm measuring that, centimeters. So if we want to just kind of go through verbally what those steps are, right? And I'll probably say it a couple different times today, but we're going to have to calculate this variance, so I want you to really get locked down. The first thing we need, remember, we were finding those deviations from the mean, so we need the mean, right? The very first thing you need to do is calculate what the mean is, or if it's given to you. Next, you go through every observation, you subtract the mean from that observation's value for that variable. Then we square all those deviations, add up all those deviations, and I guess I could have broken step 4 up here into 4 and 5 because once we add them up, we still have to divide by n, or for a sample, divide by n minus 1. Okay? So these are kind of the steps written out in terms of how we're going to calculate the variance using that formula. We're not going to waste too much time on this slide. It's really not too hard. The process of calculating the variance, we actually only have one more step that we need to do to get the standard deviation, which is, you notice, this is the exact same formula I showed you on the previous slide, but to get the standard deviation, I'm just taking the square root, which kind of makes sense because if I take the square root of sigma squared, that square root is kind of like taking it to the 1/2 power. So those cancel, and all I'm left with is sigma. So if I take the square root of this, I'm just left with sigma, which is what our standard deviation is. Okay? So same process to find the standard deviation as I did for the variance, with one more step, take the square root. Okay? And the reason why, once again, a little bit of this is some foreshadowing. Once we get the confidence intervals and hypothesis testing, we're typically going to be using the standard deviation in our formulas and not the variance. So we want to already start thinking about how we get that standard deviation to become a little more useful in some of the future formulas that we use. Okay. I kind of gave an example here, right? We had 100 was the variance. The standard deviation would just be the square root of that. The square root of 100 is 10. Okay. Any questions on that? If there's anything else in the chat. All good. So I have this old Ball State football coach salary data set. I guess it's a football team, but you can think about this as really any company almost. This could be the CEO, it could be the head football coach and the janitor, some could be the video tech guy, right? So it's just we don't have to worry too much about these variables. We're really just going to focus on this salary variable and think about what variation exists in these coaches' salaries. Now, obviously, we can see there's some variation, right? The range is actually pretty large because we have the person at the top making a lot more money than everybody else, okay? But we talked about the range isn't, the most useful measure of dispersion. What we really want is eventually we want to get this variance. So how do I do that with this data? Well, first step, we need to calculate the mean, right? So I go through, remember from last class, we just add up all these values and divide by, I think there's 10 observations here, right? The total number of observations. So add these up, divide by 10. If we do that, we get about 134.5, right? And I might not be saying the 0.5 when I'm kind of mentioning it now. I might just say that 134,000 or 134. So if I put the 0.5, that's the value I'm referring to. So we've got our mean. The next step is go through every single one of these salaries and subtract the mean. So take 489 minus 134.5. Take 150 minus 134.5. Do that for every observation. Then go back through, square all of them. Now, you don't have to do that in 2 steps. I mean, personally, I probably would not do that. I would actually find whatever that difference is. So 489 minus 134.5, then square that value. Write that value down right here. You could just make your own new column, right? Then go to the next observation, 150 minus 134.5. Square that value, write that number down, right? Do that for every observation. Then we have to add them all up and divide by total number of observations here, which is n. We're going to treat this as a population data set because of every football coach that was being paid at the time for Ball State, okay? So if I write that out, it looks a little messy, right? I wrote out exactly that process I described, right? Take that first salary, subtract the mean, square it, add to that the next salary, deviation from the mean, squared. Continue to do this for every observation. Now, you can put this all in your calculator at one time, but if you forget a parentheses or you make, forget a squared, it's, easy to make a mistake if you're writing all these things. Typically, if you're doing this by hand, I would suggest doing each one of these individually. Then once you have those numbers, then add up all those numbers, right? And I think we'll have time today. If not, we'll do it Friday. I'll show you how you can do this in Excel, okay? So if we do that, we get about 14,000, right? Now, also, the way I wrote this here, and I did this because I'll do this kind of moving forward a little bit, right? If I divide something by 10, it's the same as multiplying it by 1 over 10, right? And so sometimes when we write out these formulas, sometimes we'll see things as being divided by or multiplied by 1 over that, right? It's the exact same thing. The real reason I did it here is so I remembered to mention that, but also it's kind of hard to, if I have all this not on one line, then I put a divided by n sign. It looks kind of funky and it actually might not be as clear as once I have all this, instead of dividing by 10, I can also multiply by 1 over 10. That's the same thing, okay? All right, just checking to make sure there's no questions. So if I go through and do this, right, take 489 minus 134.5, square it, I would get 125,844. I did that for every observation. And notice, observations that are really far from the mean, right? So the mean was 134. This salary is 489. That's pretty far from the mean, right? So really extreme values are going to have a really big deviation from the mean. And then once we square that, it becomes an even larger value. However, values really close to the mean, like 124, when we look at that difference and square it, not near as big, right? Now, we can kind of think about a couple other things that are going to happen. Well, I'll walk through this first and then I'll mention some things. So we did this for every observation, add them all up. We still have to divide by the total number of observations, which is 10, gives us that 14,000. Okay? Hopefully this data set, what we can start to see a little bit of is, how does that variance, so how is it capturing what variation exists in the data set? Well, think about this, this value that's really far from the mean, it's really far above it, so that deviation is positive. But when I square it, it's also positive. Here's some values that are below the mean. But when a value is below the mean, that difference would be negative. But what happens if I square a negative number? It's also positive. So it doesn't matter if the observation is really far above or really far below the mean, it'll still add a lot to that numerator of the variance, increasing the variance, right? And the reasoning why is because all the variance is capturing is how varied is this data set? How much do these observations differ from that point of central tendency, right? How much variation exists in terms of how far away from the mean those observations are. So down here, if it's really far below, it adds quite a bit to that variance. If it's really far above, it adds a lot as well. Right? The other thing that this kind of squaring that deviation does, let's think about it this way. Let's say I had a different data set. If I had something that was only 1 away from the mean, So the deviation from the mean is 1. When I square that, I still have 1, right? But if I'm 2 away from the mean, when I square that, it actually is 4. So it adds a lot more to the variance. We keep going with these examples, like 100 from the mean, and I square that, now I've got, what, 4 zeros, so 10,000, right? So I'm getting like, as I get more and more distance between observation and the mean, we're really over penalizing extreme values in this variance, because by squaring it, right, if I have something that's really far away from the mean, once I square it, it becomes even larger of a difference, right? So the variance really captures these extreme values, like we're almost over penalizing extreme values in a data set by using that square. Oh, I know what I'm saying. So what would the lowest possible variance I could ever see be? It would be a very weird data set. Oops. But what's the lowest possible variance I could ever see? The mouse is being really sensitive now. There we go. What would happen if I had an observation that was exactly equal to the mean? Well, the deviation from the mean would be 0. No, if it was exactly equal to the mean, right? So let's say this guy right here made exactly 134.5 thousand, 134.5. When I subtract 134.5 from that, it would be 0. When I square that, it's 0. And he would add nothing to the variance because he wasn't far away from that measure of central tendency, right? So what would a data set have to look like if I had a variance of 0, right? I just talked about having kind of one observation adding 0 to the variance. What would have to be true if every observation added a 0 to that numerator for the variance? I'd have a data set that looks like what? So for every observation to add a 0, every observation would have to be exactly equal to the mean. So it would literally be a data set with all the same values, right? Could be all ones, all 24s, all 134.5s. The only way I can have a data set that had a variance of 0 is if it's literally all the observations have the exact same value for that variable, right? Now, is that likely in practice? No. But theoretically, that's the lowest possible variance we could get. So variances can never be negative, right? The lowest it could be is 0. And kind of the reason why it can't be negative, right? When we square any deviation, it'll always add a positive value, a 0 or positive value to that numerator, right? So if I ever ask you a question, like on an online quiz, and there's negative answers that are possible for the variance, right away, you know these can't be the right answer, right? Okay, so I was kind of mentioning some different properties and traits about the variance. Excuse me. So if I wanted to do something a little bit different, so I have this process that I know I can use, but there's actually another process, another formula. If we just rearrange this a little bit, we get this guy right here. Right? Now, I typically don't use this, and the kind of reasoning behind why is if we're dealing with large values and we're doing this by hand. So when I was taking a deviation squared, at least that was kind of, so for example, when I subtracted 134.5 from this, it made it smaller. So when I squared it, it was still a large number, but this number isn't as large as if I would have just squared 489. So in the second version of the formula, what we would do is we would go through every single observation and square just that value, then add those up, then subtract from it the number of observations times the mean squared. This would give us the exact same answer, and I'll kind of show you this here in just a second. We did this with a data set. This would give us the exact same answer, right? So we could do this with sample data. We could do this with population data. The only difference is instead of dividing by n minus 1 in the sample, for the population, we divide by n. We use the population mean down here. We use the sample mean here. That's the only real difference. Okay? So I'll skip this slide for now. So with these football salaries, if I wanted to use this other method, the first thing I need to do is square every single observation. So that's what I did here. All right, I just went through and I squared each one of these observations. Then I added them all up, right? So I added up all these observations squared. I then need to go back and I said, what do I want to do? I want to subtract the number of observations times the mean squared. So I find the mean, I square the mean, and now I have everything I need to plug into this formula, right? I have the sum of my x's squared. N was 10 here, we had 10 observations. The mean squared was this 18,000. I plug all that in, I get 147, but I still need to divide by n, right? Since it's population data, it was sample data, I divide by n minus 1. So once I do that, sure enough, I get the exact same answer that I was getting before. Okay? So it's two ways of doing the same thing. Whichever way you want to do is fine. I'll typically kind of use, there we go. I'm not using the mouse to scroll. Okay. So I'll typically explain it using this method, just because that way it really kind of captures what the variance is telling us and how much certain observations would be influencing the variance. The other format's fine, it'll give us the same answer, but it doesn't quite have that same intuition about what the variance is actually capturing, right? So I sometimes waste time on this. I don't know if I'm going to today, just because I want to get through a little bit more. But I told you that this formula here is the same as this one down here. I don't know, whenever I tell you something like that, I hate just being like, yeah, this is what it is, just take this, use it, which is fine, you can do that. But if you wanted the actual mathematical proof, kind of here it is, right? I can just start manipulating, kind of moving things around. So basically, I just take what's in here, I squared it, right? I get now these components, summation signs, I'm adding and subtracting things can be distributed. There's this interesting kind of trick that whoever originally solved this proof did, which is if I multiply anything by 1, so n over n here is just 1, then it doesn't change the equation. But then when I rearrange things a little bit, I can get something that looks like this, where I've got the sum of the x's over n. That should look familiar. The sum of the x's over n, that's adding up the observations, dividing by the number of observations you have, that's just the mean. And when we rearrange all this, basically it can simplify down to just this formula. So you're never gonna have to reproduce this. Don't, you know, this is just kind of, if you're interested, or if anyone who's interested in more, I'd explain it in more detail. If you, I don't know, want a Zoom meeting and geek out about math formulas for a while, but this is kind of the proof of why those two equations are the same, okay? All right, so let's say I had a data set like this. So this could be a question that I would ask, right? Maybe like on an online quiz. So first of all, if we think about what is the population variance for this commuter data set, okay? Which of these answers can I rule out right away? A, right? Because 0, what would have to be true about the data set if it was 0? Everyone would have to have the same commute time, right? So right away, we can kind of rule that out. Now, the other ones, I can't ever have the foresight of which one of these is going to be correct. I actually just have to go through and calculate it, right? So from last class, we found the mean of this data set was 45, okay? So if I have that mean, what's kind of the next step that I go through? Well, I look at the first observation, so 20 minus the mean. So I've got what? Negative 25 there. I'll square that, write that number down. Then I'll go 35 minus 45. Negative 10. Square that, it's 100, write that number down. 90 minus 45. That is 45. Square that, write the number down. Keep doing this process. Once I'm done, add them all up. And if I'm doing this, I usually like write the numbers in the data set down and then write those deviations squared just right next to it. Right? So if I go ahead and I do that, I get all these numbers. I then add them all up. I get 2,900. It's a population variance. So I divide by the total number of numbers I had, which I have 7 employees in this data set, and I'll get that population variance of 414. Okay? Any questions on that process or anything? I know I'm kind of explaining it a little bit more here than like writing everything out explicitly. So you can kind of think about what might this look like. Let's see here. I'll kind of show you how I would go about doing this. So let's try using this now. Maybe it'll start switch on us. All right, so let's go here. So I have those values that were in that data set. I would essentially take that first one. If I wrote this out all in one line, 90 minus that mean of 45, square that value. I would then add to that the next one, which was 20 minus 45, square that value. I think the next one was what? 35 maybe? I might be doing these out of order, but you can kind of imagine. I would keep doing this for every single observation, write that all out in one line, and then I need to divide by n. We had 7, so that's kind of the process I would use. Right? Now, like I said, personally, I think writing it out this way, that's okay. Like if you're really comfortable with a TI-84 or whatever kind of calculator, graphing calculator you have, you can get this all entered in pretty easily on a calculator like that. But if you have a smaller calculator and not as kind of a more complex, where you can put in a lot of these parentheses and see everything you typed in all at the same time, I would actually just use that method where if I've got all the observations here, I would just write down 90 minus 45, square that, to do that in my calculator once. What's that? Is it 2,500? Yeah, I had it here. There. Okay. Can't do that math in my head quick. Right, and I would go through and do that for every single observation. Then I would add them all up and kind of divide by that total number of observations there. Right? So either method's fine. I would say doing it this way is probably better if you have like a small calculator. And kind of the first way, if you have a graphing calculator and you're comfortable using it, it's probably a little bit easier to use that method. Okay? All right. I'm just going to unplug this since it was being weird earlier. All right. So hopefully we get switched up over here. Go back to the screen here. We had that value of 414, right? So what if I asked you with the exact same data set, what if I asked you for the sample variance? So let's say I calculated the population variance. I then go back and goes, no, that's not all the employees. That was only a small subset of the employees at this company, right? While if I instead was supposed to calculate the sample variance, what's the only difference? I still have the same values. I still have the same mean. I'll subtract the mean, square it, I add them all up. But now instead of dividing by 7, I'll divide by what? Yeah, n minus 1, so 7 minus 1 is 6. Right? If I'm dividing by a smaller number, what's going to happen to my variance now? It's going to be a little bit higher. Right? I'm dividing by a smaller number, that's going to give me a slightly higher variance. So if the answer previously I calculated was 414, I know it has to be higher than that. The only option here that's higher than that is 483. Okay? And I'm giving this as a hypothetical. It's never like we're switching from a population to a sample data set. Like it either is sample data or population data. I just want to kind of just say, well, what if you incorrectly calculated it thinking it was population data, find out later it's a sample, right? It would be the exact same process, but you divide by n minus 1. Okay? So that shouldn't be too bad. So if we go ahead, right, the exact same values, so we get the same 2,900, but now we're dividing by 6. Okay. So I want to show this. Now we're not. I'm still. If we think about creating distributions like we did with those histograms, we still haven't gotten to a point where we're creating these like nice continuous distributions. We were only thinking about them with like putting them into bins, but it's a similar idea. So if I'm drawing out distributions, the mean of a distribution would shift it, right? So here, these are all means of 0, right? So this point here is 0, positive numbers in this direction, negative in this direction. My y-axis here is just my relative frequencies, right? So you can kind of see if I had a data set where I had a lot of values that were kind of centered around that mean, that would mean I had a lower variance or a lower standard deviation, right? If all the values are really close to each other, there's not much variation, I'm going to end up with a pretty low variance or standard deviation. Okay? What that's going to mean is that a lot of these values that are centered around the mean, right? That mean was 0. So these values that are around the mean will be very likely for me to see. Right? If there isn't much variation in the data set, that means I know most of the observations will be right around that mean. So if I was to create a histogram, the bars that were around 0 would be really high, right? Or have a higher relative frequency, okay? As I get a higher and higher variance or a higher and higher standard deviation, what's going to happen is, well, that means I have more variation in my data. So it means that not only will I see values that are centered around the mean, I'll also now see values that are pretty far from the mean, right? So as my standard deviation goes up, we look at the highest one, my distribution is kind of flattened because the values around the mean are now less likely, right? Their relative frequency is lower, and the values very far from the mean, right, this gray line, the values further from the mean have now become more likely if I have a data set with a higher variance. Right? And we'll see this photo a couple other times during the semester. I'm kind of introducing it here now. We haven't talked about these nice continuous kind of distributions, but the general idea is that the mean would shift these distributions, and the variance or the standard deviation, as that variance or standard deviation gets closer and closer to 0, we end up with a really, really peak distribution because all the values that are centered around the mean are going to be the most likely values we see from that data set. A higher and higher variance or standard deviation means it kind of flattens that distribution, making values further from the mean also just as likely as seeing those near the mean. Okay? Like I said, we'll revisit that kind of discussion later on, but I wanted to introduce it here. Okay? So how can we do this in Excel? So we'll do a little bit of work in Excel today. Shouldn't be too bad. I'm actually going to sit down here. Do this so I can type a little bit easier. Someone trying to get in the door, just making noises over there. Okay. So let's go into Excel, and we can just open that blank COVID file for right now. What do I want to work with? We can use that state level data. We can keep working off the same data set. So down here, I'm going to add a few things. Actually, I'll show you a couple other things just to get a little bit of Excel. If I want to insert a column here, so like I don't want to have to scroll all the way down here and put my work here, but I want to make sure that I keep all the work that we previously did, right? So if I right click on a column and I go to insert, it'll insert a column for me. I can do the same thing with rows, but for right now I don't want to do that. I want to insert my columns, give myself a little bit of room to do some calculations, okay? So let's say we want to find the mean, median, and the mode, right? So I had these state level COVID deaths. Like I want to find what's the average number of deaths across these states. Well, we're not going to have to do this by hand. I talked about, you can envision, I could add up all those values, right? And then divide by the total number of observations, which I conveniently have laying in this cell down here. But I could also have found that by using that count function and then just selecting the variable as well. So notice I don't have to do this in two separate cells. I can put multiple functions in the same cell and use whatever values they return. So this will go through and add up all these observations. and then divide by the total number of observations that's returned by this count function. Okay? So if I do that, I get about 2,600 on average. That's how many deaths there are from COVID in each state. But I can also do a much easier way, right? Which is actually, instead of mean, Excel calls it finding the average, right? Kind of those two terms, thinking about those as interchangeable. Okay? So if I want the average of what? Well, I want the average of this variable. So once again, the shortcut here that I'm using, if you forgot, Control Shift or Command Shift on a Mac, hit the down arrow, hit Enter, it'll pop me back up, right? I got the same value there. So just two different ways of doing the same thing, okay? If I want the median, it's pretty easy as well. Equal sign median, right? I don't have to like arrange it and cross out the highest, cross out the lowest, do this all by hand. Especially, I only have 52 observations here, but what if I had, 1,000 or 2,000? Well, I just select that variable, right? Control Shift down arrow, then I hit Enter, and it'll return to me the median. So just looking at this, kind of doing a callback here, my mean is much greater than my median. So what type of distribution would I say state COVID deaths have? Right skewed, yeah. Because my mean is greater than or to the right of my median, right? I don't even have to see the histogram that we created from last class, but if I did want that, if I have the file open still, yeah, here we go. Have a long right tail, right? Really long right tail. It was a weird distribution. So we found the median. Mode is just equals mode. Now I think here it's probably not going to return this anything because I doubt. Yeah, so there's no two states that have the exact same number of COVID deaths, so this doesn't work great for this example. You can imagine a data set where I had repeating values. That equals mode would return to me the mode. Okay. If I then want to find the variance or the standard deviation, and I can auto fit, remember, by double clicking that in between the two columns to fit whatever in them. So here, we've got two options, right? And you'll see there's a bunch of different variances. The ones that you should be using is var.p and var.s, okay? var.p would be treating this as population data, which we should have every single kind of death that's occurred from COVID here, so we do have population data. I then just select the data I want to find the variance of, and sure enough, it goes ahead and calculates that for me, okay? If I had sample data, the only thing that changes there is I replace that .p with a .s, okay? So I don't think that's anything too wild, anything too crazy. Should make some sense. What if I want to find the standard deviation? Well, what did I say? If I have the variance, how do I get the standard deviation? I just take the square root, right? So in Excel, how we take a square root is SQRT, so square root, and then what number do you want to find the square root of? I click on that number that I already have in the other cell, hit enter, and it'll give me my standard deviation. Now there's another way you can do that. I just more so showed you that so I could show you that square root function because we'll use that later on in this course. There's also STDEV.P will be the population standard deviation. I then select the data, and sure enough, I get the same value. It's rounded here, so I could go in and format it so that it goes out to 5 decimals and I have the same value. Right? I'll show you that again. So STDEV.P, or if I had sample data, just like with the variance, I just change that P to an S. Okay? So I think that's pretty easy. I mean, so you can kind of see a lot of this stuff that we have to do by hand, calculating means, calculating variances, especially doing this with larger data sets. I mean, you can save an infinite amount of time using Excel instead, right? And there's a couple different ways of doing that. You can use that STDEV. You can use that square root if you find the variance first. There's kind of different ways of getting the same values. But I think this makes life a lot easier, right? And I've kind of, I got a couple minutes left, so I'll go on a little side here. I've kind of decided that, you know, when I'm giving you these, when we get to the exams, right? If you've been putting the time and the work into the Excel assignments and getting good at using Excel, I'm okay if you're using Excel while you're doing that exam. Like, that's a tool you're going to have available to you anyways. You know, I think it's good that you can, you know, do some of these problems by hand. If it was me, when I'm doing the Connect homework, I would try to do it all by hand, right? Because it's still good that we understand the process, right? Because later on in the course, there won't be as many obvious, like there won't be as many shortcuts that we can do in Excel. Like we'll still have to use Excel to type in the formulas for us. And so getting used to doing things by hand and taking these formulas and doing it by hand will really be important once we get later on in this course. But yeah, if you want to get good at using Excel, right, I'm okay if you're using it essentially as your calculator when you're on that exam, right? I mean, it's a tool, right? You need a calculator, why shouldn't you be able to use an even more powerful calculator? That's kind of my opinion on it, okay? Anything else I want to say? Oh, so I usually, I was kind of noticing before class today, and because I changed it from what the previous Learn Smart was, I think the previous one I had to do at the end of the day. And I think I did say you should have the next one done before we start class Wednesday. But I'm feeling kind of nice, and I noticed a couple people hadn't gotten and done it. So I'll extend it to the end of the day just in case there was that confusion, because I was looking at the first one and it was set to the end of the day. So if you're kind of confused on that, I'll open that up after class so that if you haven't done it, get it done by the end of the day, get those easy points. Okay. Any questions kind of for me before I let you guys get out of here? I'll open the chat so I can see if there's any. All right, so group one, we're looking at that seating chart. You'll be able to come in-person class on Friday. And then next week, everyone who's here today, group two, you'll be able to show up on Monday and Friday of next week. Okay? I think that should cover it. I'll get an online quiz posted after class today. I should get the YouTube video up there as well before I kind of start my next classes, okay? I will see you guys. Well, some of you I'll see Friday, some of you I'll see Monday, all right?